So we've almost completed the analyze phase yesterday. Recap, post define measure, and the analyze phase we looked at establishing the process capability and defining performance objective, setting up a benchmark, and then we looked at identifying variation sources and looking at identifying critical X's that we have already identified, right? And then we learned how to prioritize using the hypothesis test that we'll have to perform, right? And just to give you a little more detail on the hypothesis testing, if our data is attribute or discrete in nature, first we do a Pareto chart, and then we do a chi-square test to check if this particular X is statistically significant towards Y, right? And if it's a continuous Y or a variable Y, then we have different tests that we perform. So the first one is box plot to look for variation and mean difference within the variable. And if we think one of these X is good for analysis, then we go ahead and check if this is statistically creating any significance to Y. And if it's just one variable, we look at a 1T test. And if it's two variables, we go for 2T test, paired test. And if it is anything more than 2, we go for an Anova test. And this is in case if the data is normal. If the data is not normal, then we go ahead and perform a parametric test, which is something I would like to show you once again on Minitab, so that you get a little more idea on how it is done. Yeah, so here you go. So this is the Y, which is yield. And what kind of metric do you think this is?
This is
Data.
We have vendors. You have yield. You mean like what's the?
What kind of data is it? Is it discrete? Yes. It's a continuous data, right? Because
okay.
it is measured on a scale. You have any number. It's not really yes or no, or it's not really the number of defects or anything like that. So it's
right.
Continuous data, right?
Yes.
The first thing we do is we look at box plot. This is something we did yesterday. I'm just trying. And we select the yield. And then we select this as a vendor. Right. So we get to this stage and we know that between vendor A, B, C, and D, there is a variation and there is a difference in the average, right? This is what we observe the box plot, right? So to a conclusion from here is that vendor B, for example, has the highest mean or average, or it has the highest yield, and also in terms of variation, the vendor B has the highest variation, right? So this is the first analysis that we do when we get the data, right? And the second thing I look at is whether this data is normal or not, right? And then I go to stats, I look at the normality test, and I pick up the yield. And what's my p-value?
0.78.
Right. So what does that indicate?
That it should be normal distribution. It's valid.
Right, absolutely. So it is normal distribution. So now let me look at my chart here, right? Now I realized is that my Y is continuous, right? I'm trying to select which is the best hypothesis test should be used to determine if this X is significant or not, right? The first thing I look at it, Y, which is a continuous Y, right? So the yield is basically measured on a scale. So that's Y is continuous. I hope you can see this chart, right?
Yeah, I can see it.
Okay. And then I look at my X. What is my X? My X in this case is vendor, which is classified as A, B, C, and which is a discrete or continuous. It is not measured on a scale, right? So it is a discrete X, right? Did you understand that part?
I'm sorry, what?
Yeah. So I'm trying to look at X and Y, right? To figure out
Yeah,
any
your
statistical
X,
difference between
your
vendor and yield, right?
right, your X's is your vendors, and your Y is your yields, which is the hard factual data.
Absolutely. So my question is, when we identified the yield as continuous data, and what do you think the vendor is?
It's the when you say continuous, continuous equates to discrete, correct?
No, there are two kinds of data, continuous data and discrete data. Continuous is anything which can be measured on a scale.
Okay,
Right?
1 second, 1 second.
Yeah.
Say that again, please.
So there are two kinds of data. One is attribute data or a discrete data. And the other one is continuous data or a variable data. A continuous data is nothing but anything which can be measured on a scale, right? A weight, a length, which can be broken down into different numbers. For example, if you look at here, yield, it is 91.4, 94.6, 92. It could be any number, right? And on the other side, a discrete data would be, it could be A, B, C classification, or it could be yes or no classification, or it could be the number of defects or number of errors, something like that. Those things come under discrete. So now I have my X and Y here. As you understand, Y is yield and X is vendor. And it is, since it's measured on a scale, it is a continuous data. And vendor is classified as A, B, and C, right? So that's a discrete Y.
Okay, so your vendor, I mean, yeah, but your vendor is your X data.
Absolutely. So I'm asking what kind of data is it? It's a discrete data, right?
It could be discrete because
Yeah, it is discrete.
It's not continuous. It's not hard numerical data.
Yeah. So
it's more classification.
Right. So it is a discrete one, right?
Yes.
Okay. So I'm looking at my hypothesis testing, right? What do I do when I have a continuous Y, and then I have a continuous X and a discrete X? So in this case, it is a discrete X. Do you agree?
Yes.
And a continuous Y, right?
Yes.
Now, then I come down. I need to assess whether the data is normal or not normal. That is the next one.
It is normal.
It is normal. That's something we've already checked, right?
Yes.
Now I select which is hypothesis testing, which I should be looking at. Now there are three. If it is a normal data, you have one sample t-test, two sample t-test, and one way ANOVA. So how it works is, if I only have one variable in X, I use the first one. If I have two variables, then I select the second one. If I have more than two, then I go for ANOVA. So in this case, we have three variables. There is vendor A, B, and C, which is more than two, right? Then I use my Anova test, right? Then I select the one-way Anova. I choose my responses yield. I choose my factor as vendor, and I click OK. So this is how each of these vendor is plotted. Let's look at the p-value, right? And the p-value is showing as 0.02, right? So if you get a p-value which is below 0.05, your null hypothesis is rejected and your alternate hypothesis is accepted, which means that there is a difference between X and Y. I mean, which means that X is making a key difference to Y, or X is having a direct impact on Y, which means this is a very critical X, something which we need to analyze. There is a difference in performance.
Sir.
Yeah.
So, excuse me for cutting you off. Hello?
Yeah, I'm here.
Okay, I'm back. Sorry about that. Thank you.
Okay, no problem. So I did my Anova test, right? Because my X is discrete and my Y is continuous. I want to see if the vendor has a direct impact in the yield or not, right? And if I get my p-value as 0.02, which is less than 0.05, right?
Yeah, so that means you don't have normal distribution?
No, so we are currently doing the hypothesis testing, right? We are trying to assess, whether the vendor has a direct impact on yield or not.
Okay.
Right? Normal distribution is something we've already checked, and that p-value was above 0.05. So the distribution is normal, right? So based on that, we took a decision.
Okay. Yes.
We chose which test should be used, right?
Okay.
And
yes.
Under normal distribution.
Yeah, we're doing ANOVA.
Yeah, we took the Anova.
Yeah, because we have more than two variables.
Right. And then we do the test.
So what does that mean? What's that p-value? What does that mean?
Yeah, so now the p-value means if it is below 0.05, vendor as a variable has direct impact on yield, which means that the performance between vendor A, B, and C are statistically different. Which means you need to go ahead and identify the root cause and why it is happening. And this could be one of the reasons why you have a lesser yield. Right? So anything, so just understand this, anything which is below 0.05, consider this as a critical X. So vendor, we will keep it as a critical X.
So that means that if the p-value is below 0.05, then the X, or it doesn't necessarily, yeah, then the X value has a direct impact on the yield.
Right, and that's a critical X.
It's a critical X. Yeah, it becomes a critical X basically to direct your focus on those X values.
Right.
And address them accordingly.
Yeah, so in Analyze, what we do is we try and prioritize the list of all X's. So during the measure phase, we come up with a list of X's. And in Analyze phase, what we are trying to do is we are trying to prioritize which are the key X's which will have a significant impact on Y. And that's something we've proved using a hypothesis testing that we did. Okay, so we'll do one more example, right? So I have an example for, right? So we have two variables here, right? For the same data. The data is.
Yeah, so we're gonna do the test for two.
Yeah, so we're gonna go to Anova. Not Anova, we go to sample t test. Right? We take student 1, student 2. I click OK. I get my p-value. And can you tell me the result of this one?
Well, this can't be good because the p-value is above 0.05.
Yeah, so if the p-value is above 0.05, which means that there is no significant difference between the performance of student 1 and 2. So you can just ignore this as an X. So student has no impact on the final output.
Right. So that's what, so X value it's not a critical X value.
Right. So it's not a critical X value. You can just ignore. You can just move ahead with the analysis, right? And this is how we identify. And so if I have both my X's, right, as continuous, then we will go ahead and do a regression analysis, right? For example, let's say my yield is Y. Here, this is continuous. And I'm looking at this as a performance, right? As my X, sorry. Now, both these measures are continuous. When I have this kind of a scenario, then I will go ahead and do a regression analysis. Again, you look at the p-value in the regression analysis and then you take a decision. Right? Same way, you go to regression, fit the regression model and select X and Y, and then you run a regression analysis. Is that clear? You want me to do it once? Let me just perform.
No, I understand. So the vendors is the X value, the yield is your Y value, the same. And basically what you're telling me here, the same thing, if the p-value is below.
It has a different one. So let me just check the responses yield. I'm taking vendor D. Suppose this is my X, right? Click OK. Right. So I get something very key. So if you look at here, yield, right? And you have positive sign, right? When I have a positive correlation or a regression between X and Y, which means that it has a positive impact, which means when X changes, Y also changes. So it's important for us to go ahead and further study and consider it as a critical X. And p-value is also, yeah, in this case, there's no p-value. You basically look at a positive correlation or not straight away.
Oh, this is a regression analysis. What's the purpose? I don't get it.
Regression analysis is done because when I have my X and Y continuous, right? In this case.
Okay.
Right? Then I use my regression analysis, right?
Is it correlation or regression?
You can use a regression analysis. Basically, it will give you a correlation coefficient. Let's say what it is right now. Yeah. So correlation coefficient. So you get a number. Where that comes. Yeah. Yeah. There you go. 72.4. So that's the correlation coefficient number, 72.4. If it is anything above 70, right, it tells you there is a positive correlation between X and Y. And this is not the very good data. I just took it up, just took from here, yield versus vendor, and still gives a correlation which is above 70. Right, which is a good number. So just understand, there's only one thing that you need to understand. If there is a positive sign here instead of negative, right? Vendor has a direct impact on yield, which means you can go and further study this as a critical X.
So this is, wait a minute. So this is the same deal like a hypothesis test?
Right. This is also a hypothesis test. This is used when you have both X and Y as continuous.
Okay, can you go back to the table? To the data table? So, okay, so yeah, so, okay, so but what are you using for X? X value, it's the vendor.
Now I took this one, vendor D.
Oh, okay, that's what, so that, okay. So we took C4 and C6?
C4 and C6, right.
Okay, so yeah, that would be, both of them would be, both values would be continuous.
Yeah. This is not a very good data for regression analysis. I just wanted to show you.
Sure, but what's the purpose of it? Well, I mean, what?
The purpose is when I have X and Y, right? Both are in continuous scale. In this case, yield is, in continuous scale, right? And X is also in continuous scale. This can be anything. It can be weight or
Yeah, no.
that you're trying to
Okay.
measure, right? You're
Okay.
putting on a regression or a correlation model. And if it is going up, the direction it's going towards the top, then there's a positive correlation. If it's coming down, then there's a negative correlation, right?
Okay, okay.
Correlation, you consider it as a critical X. Very simple. That's all.
Okay, yeah.
Okay, does that make sense? Okay, perfect. So that's about hypothesis testing. And if the data is non-normal, you go for a test, one of these. Right? The first one is obviously if it is one variable, you go for one sample, two variable Mann-Whitney test, or you can just straight away do a Moore's median test. I think I have an example here. Yeah. So this is a non-normal data for me. So let's do a check. Normality test. We select time. So let's see. Yeah. P-value is less than 0.05. That's my inference, which means the data is not normal. Right? When the data is not normal, I look at my graph. It's a discrete X or not. The X is call center 1, so it's a discrete X. So then I choose one of these tests. So let me go and try the Moore's median test for now. I go here, I go to known parametrics, and then I select the Moore's median test. Yeah. First one, I put the handle time. Here I select the call center. Then I get my p-value, which is less than 0.05, right? So what does that indicate?
If you're doing a hypothesis test, it means that it's going to have a direct impact on that. X value is having a direct impact, and X is a critical X.
Yeah. So statistically, this X is significant. It is a critical X. Yeah, absolutely. Right. And let's take another example also on the discrete Y and discrete X. This is something we discussed in brief yesterday. Let me see if I have, yeah, so this is another example. So in this case, I have two age groups, old and young, and whether we hired them or not hired, right? In the old category, did we hire? Not hire. And this is how we populate number for a chi-square test. So in both the cases, the X is old or young for the age group. Y is hired or not hired. Both are Y, right? And both are discrete. So we go to the statistics. First, we do a Pareto and figure out, and after that, we summarize that number and come here. And then we go to tables. We select chi-square and select hired and hired and click OK. So you get this, and you have p-value is right, which is more than 0.05, which means that
normal distribution
does not have any statistical significance, which means you can just ignore age group. That's not really a criteria on hiring. Hiring is not depending on old or young. So there's something else that we need to look at. So you can just ignore, you not
Yes.
waste time there. I hope it's kind of clear now for you.
Yes.
Okay. So this is a very, very important chart, and it's a very important test as well. I mean, not just for doing this project, you can use it in your regular work. Any data that you are referring, instead of arriving at a wrong conclusion by just putting it on an Excel bar graph, you can always go and do a hypothesis testing to really figure out if this X that we are measuring and spending so much time, does it really have an impact on the metric? And if it's not, you can just move on to something else.
Am I gonna question? Okay, understood. Am I gonna get am I gonna get these slides before the test, or?
Yeah. So
I mean, you know, because it's a lot of information. I'm taking notes, but you know what I mean. We're also moving. We're moving at a good pace. I like the pace that we're moving, but it's just, you know, it's a lot. So I'm afraid, you know, if I get some questions on the test about this, you know, and let's say this testing, I'm sure I will. I'm gonna be like, you know.
yeah, you will get a since.
Uh,
All right. So I'll quickly, you know, read through what are we going to do in the improve phase, right? Now,
okay.
identify critical access. That is the final step we are at. All right. We have identified it through statistics, right? So if you remember what I mentioned earlier, first we understand the problem, which is a practical problem. Then we convert that into a statistical problem. Then we come up with a statistical solution, which is almost what we did during the analyze phase. And the next part, we, from the statistical solution or the analysis, the critical access that we've identified, we go ahead and convert this into a practical solution, which is what we do in improve, right? Now, so now we have all these critical access identified. We start developing potential solutions against each of these X's, right? And then we evaluate, select, and optimize the best solution which is possible to implement in order to improve the X factor or the variables, and thus improve the yield or the metric of the project that we are trying to drive. And then we will also develop a to be value stream map. We will, in most of the cases, we make changes to the process in order to drive improvement. Then we come up with a to be process map, and we test these solutions that we are proposing for a period of time. For a Greenbelt project, it's ideally we test it for a month, and we do the pilot, and then we wait for the results. We calculate few things. One is the metrics that we calculate, whether it's improved or not from practical solution point of view. We also calculate the sigma value, the Z value, or the CPK value, something that we've done when we did the process capability, right? To see if the improvement has happened or not, right? And then we also assess the risk of implementing these solutions through something called Fmea. Fmea is nothing but failure mode effective analysis, right? And then we do the process measurement once the improvement is done.
Okay.
Right. So any questions? I hope that's quite straightforward on how do we do the improve part. And there are some techniques and there are some tools that we use during the improve phase, which is something we will go in detail in the next session.
Okay.
Have you heard of Fmea before? Have you done it in your?
What?
Fmea, the failure mode effective analysis?
No.
Not really. Okay. Okay. Kaisen, I'm sure you are familiar with? Continuous
Yes.
improvement. Okay. How about 5S?
Yes, we work.
Okay.
We have that implemented in our site.
Okay. Non-value add analysis.
Yes.
You've done that, right? So pretty much, you know, most of these, but we'll obviously go through some of these. And these are
Sure.
some, you know, ways in which we identify solutions. We do brainstorming. We do a 5 why analysis. Have you heard of that term?
5Y.
Right.
I've heard of it. Yeah.
Yeah. So what you do is you take a particular problem, or you take one of the X, right, which we know
Yeah.
that it's X, and we ask 5 questions. 5 times you ask why.
Yep.
Why is the metric low? And you get an answer, and you ask again why on that. And by end of 5 whys, you get a solution, right? So that could be one of the things that we can use. And value stream mapping can be one, where we look at all the non-value adds and we try and get rid of the non-value adds, which could give us a solution. There are multiple things that we can look at. And okay, let me check if I got my access. Okay, so let me just read through what's on the slide. So the key roadmap for improved phase, there are 5 roadmaps that we've kept in place. The first one is developing potential solutions. So based on the validated and prioritized root causes, we develop potential solutions, right? And there's some of the techniques that we use is 5 analysis there. And then we prioritize the best solutions that we've received, right? We put them in a priority matrix. Let's say based on impact and ease of implementation is one example, right? We put all the solutions that is identified and we create a criteria of prioritization, and we start implementing the one which has the top priority. So that's the second roadmap or objective of improved phase. The third one is evaluating risk. So what we do is we assess risk in implementation of each of these solutions. So this is where the Fmea tool comes into picture. So we look at all the failure modes of each of those solutions, and we assess them on 3 parameters, right? One is severity, occurrence, and detection. So these are the 3 parameters we look at. I will show you the template and how do we collect those information, and we give a priority number based on these 3 factors.
I cannot see the screen.
Yeah, you cannot see the screen. I understand. So I haven't got the host access yet, but I'm just giving you a little bit brief, and I'll give you in the next session whenever I'm able to share the screen and give you the details. So the Fmea tool, in fact, we will go through in detail, right? We will do a quick exercise also based on from your process standpoint, so that you understand it better. Okay, so the 5 roadmaps. So the first one is developing potential solution, prioritize best solution, evaluate risk, which is what I was just talking about. Then we do a pilot implementation. We run it for at least a month for a Greenbelt project. We collect a sample data for about 1 month, and then we assess whether the solutions that we have proposed is being effective or not, right? And then we do a Tollgate review. Tollgate review is done with the sponsor or black belt, the project leader, to approve the improvements that we've done in the last 1 month. And this is the 5 different steps that we do in the down a potential X's, and then we did a few analysis to identify critical X's from the X's that were identified in the analyze phase. Now, in the improve side, what we're trying to do is the solutions identified, or the key X's, critical X's that was identified during analyze, we're trying to convert that into a practical solution mode. So what we will do is we will develop potential solutions against each of those X's. We will evaluate, select and optimize the best solutions out of it. Then if required, we will develop a to be value stream map from the existing process map. Then develop and implement a pilot solution. So before we go ahead and start improving the process straight away, we will do a pilot for a month, and then we will take the results and see if the solutions that we proposed holds good or not, right? And then we also see to that the project goals that we had listed during the define phase is achieved or not. Then the next phase is implementing solutions. Then complete the improve gate, right? And then we jump into the control phase. So let's start with improve on some of the key tools that is used in improve. We'll see. So like we just discussed, the key objective is to validate solutions. So key deliverables would be potential solutions. We do Fmea, which is nothing but failure mode effect analysis. Then we do a risk assessment and a pilot plan. Now, when we are in improve phase, some of these questions we start asking. So the first thing you do is we get all the SMEs and all the key project members that we've identified in driving this project to a room. And then we start looking at the possibilities of eliminating something if there is a non-value add in the process, which was identified during the process mapping. Can we eliminate? Can we combine some of these steps to make it look better? Can we simplify some of these processes? Can we rearrange something that we were doing initially? So these are some of the questions that we start asking, right? And then we go by the critical axis identified. Again, we do further brainstorming on each of those. So we will see some of the techniques that is used. And whenever possible, we will always go for the cheapest solution that's available to implement. We will, through a Six Sigma project, it is very unlikely that we will go ahead and invest on a technology to improve a process. That's totally different. We try and improve the existing process using driving continuous improvement or identifying the defects and eliminating the defects. In some cases, we have specification limit given by the customer. We try and either stretch the specification limit or try and reduce the defects. However, the variation remains the same. So an ideal improvement would be something like this, where we had a process with higher variation and then we reduce the variation, and we also focus more on the target or the average value. Now, for a good improvement plan or a solution that we put across, there are two key factors. First is quality of the solution that is proposed. Second is acceptance, and which is very important in improve stage. And these two put together is what something we get called effectiveness, which is E, right? Quality of the solution is important. Acceptance, we have to start doing a lot of change management within the system, right? Any changes or any recommendations that we provide can have a big impact to the people who are actually working on the process. It could be upstream, it could be downstream, right? And the stakeholders might have reservations in changing something in the current process. So there's a huge change management initiative that we have to initiate when we propose a solution and start implementing something, right? And then only we will have a very effective solution that we can implement. Now, brainstorming is definitely one of the tools like we discussed, and we try and generate as many ideas as possible, right? We get into a room, we leave all the other barriers, and then we just allow free flow of ideas. We invite everybody to contribute in some or the other way, and we will keep the group as mixed as possible. I mean, we get people from all the streams if we can, and then we clearly focus on critical X's, because we have done a lot of hard work in identifying the key X's, and we should try and stick to that, because the discussions can go to any stream, and then we do not want to redo the same kind of analysis that we did, since we will stick to the critical X's and the critical to quality. And these two factors is something we should keep in mind. And keep a very small group as we can. If we end up having a bigger group, and obviously discussions will go haywire, and it will not be able to get the right solutions in place. And we will try and prevent biases, and because we will try and stick to what the data says, and always that mediation is very important, and manage time and scribe all the details. We invite a solution obviously from each and every participant. Right? Some ground rules that we would like to keep. There are no dumb ideas, right? Any idea can be good. So we always welcome good ideas and never criticize other people's ideas. It's also very important for our teamwork to be effective. And we build on other people's ideas. Sometimes some of these ideas may not directly relate to what we are trying to do, but we will try and build on from what kind of ideas they come up with. And the more creative ideas, the better. Currently, the whole dynamics of the business is changing, right? It is not the traditional way of working anymore. There's a lot of disruptive technologies that's coming into business, and we are completely moving away from the traditional way of looking at things, and there are much more creative way of implementing new solutions. So we should be more open to that. Any transformation digitally possible, we should definitely try and work it out within the budget that's available. Right. Another tool that is very effective is the 5S. We sort, which is we put things in order. We set properly arranged process, shine, clean, eliminate any kind of waste available in a process, which is there in the process, and then we keep it clean, standardize as many processes as possible, so that when we do a repetitive task on a particular process, we never end up making errors. So standardization can help there. And sustain. So this is 5S tool. I'm sure you are pretty familiar with this. This is the basic in any manufacturing business that we follow. And 5-way analysis is another one which is not listed here, which is something we discussed the other day. And always, if you have a problem, ask 5 whys. 5 times you ask why, and I'm sure end of 5 times when you ask, you will definitely reach to a solution. Right? Another very important tool, which is the failure mode effective analysis. Do you have any questions before we move on?
No, it's fine.
Okay. Now this is a very advanced quality planning tool used to evaluate potential failure modes and their causes. This is not really a solution generated as such, but this provides a huge insight into the solution mode. We start thinking very differently. We will see it through a template. And it helps us to prioritize the potential failures and the solutions that we get. It's a very disciplined methodology, which is used in most of the industries for all kinds of processes. Yeah, like it's mentioned, it's not a problem solver, but it is used in combination with other problem solving tools. Now, let me show you a template. So there are 2 kinds of FMEA. One is process FMEA, and the second one is design FMEA. Right? So you already have a process in place, and you have multiple steps that is required to complete a process. And we can do an FMEA study for each of the steps in the process, which is one way of doing it. And the second way is design FMEA, when we try and design a product, or when we try and design a new process from the beginning, any step that should be involved in designing a product or a process, we should go ahead and do a failure mode analysis. So any risk assessment that we do, which will help design the best process that is possible. These are the two kinds of FMEA. Now, let me just show you what we do. So before, I hope you can see this template.
Yeah, I can.
Now, this is how a typical FMEA looks like. So the first thing, we put a project name, and then we put the date on when it was done. We list the number of people who was helping us with the this analysis and who prepared it. Right? There are few terminologies that we should keep in mind, and I will explain one by one. So the first thing what we do is, we have a template here, and we have a list of columns, and here we have a list of rows, right? 1, 2, 3, 4, 5. First thing we do is, we from the process map that we have already developed, we put in all the process steps here, one by one, right?
Okay.
Let's take an example from your world. What could be your first process step in any of the time delivery or any metric?
In any what?
Yeah, from any of your process, can you just tell me one of the steps, one of the process steps?
Let's say, yeah, but I mean, okay, what activity? Let's say activity will be like production line feeding.
What's that?
Give me 1 second.
Placing purchase orders, is that okay?
Okay, so we can say, yeah, let's say we're placing purchase orders. So first one, so you want me to go through each step of the
No,
process?
we'll just take one step for now as an example.
Okay. All right, so place an order, placing the PO.
Yeah, so placing an order, right? Now, when you place the order, so placing order is again a generic step, right? So the first activity in placing an order would be validating the RFQ. For example, I'm saying, right?
Right.
So validate RFQ, right? That's the first step. Now, the second column, if you see, potential failure modes. So we are asking a question: what are the ways in which this particular step can fail? Right? What are the ways in which this RFQ validation fails? Right? One example would be not receiving the complete RFQ details.
Not receiving it on time, not receiving the complete RFQ, the buyer not reviewing the RFQ properly,
right?
And not translating the information from the RFQ onto the actual PO properly.
Absolutely. So we can really come up with multiple failure modes that this process or this particular activity can have. Now, we also, then the next step that we take is potential failure effects. Now, for each of these steps, right, each of these failure modes that we've identified, we check what are the effects. For example, if you do not have the price information in RFQ, or if there is an incorrect price information, obviously the impact is going to be an incorrect PO going to the supplier, right?
Yes.
So that's the potential failure effect. Now, there is something called SCV written here, right? And that's called severity. So from the impact from this particular failure mode, we have a score that we put, it's called severity. So if I skip to the next tab, there is a ranking from 1 to 10, right, for the severity. Now from here, if the severity is really high, the number would be a 10. Similarly, we have from 1 to 10, there's a ranking system, right? So based on the impact that particular step failure can have, we pick up a number from here, right? Anything between 1 to 10. Right? And each explanation is clearly mentioned here in the template. Right? If there's a complete production line stoppage and there's a work stoppage, which can have a huge impact on on-time delivery or cash flow or giving the final product to the customer, obviously you go ahead and rank it between 8 to 10. If it's a minor disruption, then we can rank anything between 5 to 7. Right? If there's no impact at all, then we can probably look at 1 to 3. So based on that, for this particular step, based on the impact that we've identified, we put a score. Right? So the next is potential causes of failure. So then we start asking questions. What are the reasons why these effects or this particular step is failing, right? Then we start looking at the upstreams from where the input is coming, so that we really understand what could be the potential causes of failure. Now, the second score type is occurrence, right? And how often does it occur? That's a question that we ask in the occurrence phase. Again, we have some ranking and few parameters on how we should go ahead and do the ranking for it. Right? Here again, for a high risk, then we go ahead and pick up a number which is from 8 to 10. And for the moderate ones, we go ahead with 4, 5, 6, and then for low ones, 3, 2, 1. Right? So we pick up the second score. And the next question we ask is current process control. Are there any current process controls in place? And based on that, we understand if this happens, can we detect, how often can we detect this, right? Are we in a position to detect if this failure happens? Is there a checklist in place, or is there a control mechanism in place so that we detect? If we don't detect, it's another bigger issue, right? So we have another score, ranking based on the detection. If we are able to almost certainly detect the problem, and then we go ahead and select 1, very high, 2, 3, moderately high, and then based on this, we get another score. Now, and then we multiply these 3 numbers, which is severity, occurrence, and detection, and we get a number called RPN, which is called the risk priority number. Right? So let's say 5 each, 3 5s will become a number that we get here. Okay. Any questions in it?
No. What's this RPN? It's a
risk priority number. Risk priority number.
Sure.
And then we start getting, for every step, right, we start getting a risk priority number. And how do we prioritize these failure modes is based on the risk priority number. The higher the number, the higher impact this particular step can have, or this particular activity can have. So then we start prioritizing based on this number and start putting in some recommended actions. So how do we avoid this particular failure? Then we put a recommended action, and we put a responsible person's name and the target date. We also monitor an action taken against each of these recommended actions. And then we do a post FMEA, similar activity. Once all these recommended actions are complete, we again take a severity, occurrence, and detection score, and then we validate the RPN number.
Okay.
Right? And this is a very, very important, even though it looks very simple, right? Once we start doing it on a business, we really understand what kind of risk we are running this business with. We get multiple ideas, we get multiple failure modes, then we put in so many recommended actions, and it really does wonders to any process that we have used. From my experience, I have used this tool quite a bit, and it really worked very well. A lot of projects really come out of the ideas or the problems that we see here. Right, so this is one tool. I'll tell you where it is used in Improve now. Now, what we do is in Improve, what we do is once we come up with all the solutions, right? So there are two places where we use FMEA. One, on the process steps, we look at the entire process map and put in all these failure modes, and we identified wherever improvements required, we put in the recommended actions, and we calculate the RPM. Second, we come up with a list of potential solutions, right, based on the brainstorming activity that we do. And against each of these solutions, again, we should do an FMEA. For example, if I go ahead and implement this solution against this activity, what are the ways in which this solution can fail? So what we're doing is we are doing a risk assessment with the FMEA tool, so that upfront, before even implementing anything, we are putting in we are identifying any kind of failure that can happen to a particular solution. Now, we can also, from the failure modes identified, we can also classify them into through a cause and effect diagram or a fishbone diagram, like I mentioned earlier. And then we can start categorizing into different buckets and start fixing the issues. That is also a very good way of identifying solutions. Right. So these are some of the examples of potential failure causes: omitted processing errors, any missing parts, wrong parts, misoperation, adjustment error, poor process control procedures, bad recipe, lack of safety, hardware failure. There are tons of issues that we can identify if we are able to start thinking on potential failure modes, in any way in which a process or an activity can fail. Something we've already discussed. We multiply severity, occurrence, and detection, and we get something called a number. And this is the template that we've already seen. And some examples on how some of the process controls can be implemented. Basically, standardizing your work instructions, procedures, fixtures and jigs, mechanical interference. You have mechanical counters. You can put up a sensors. You can come up with your own job sheets, process packages. So most of these controls, if you see, these are all very very easy way of doing things. We don't really go ahead and buy a technology to fix a problem. We try and clean up as much as possible, and without spending much money, we should be able to put controls in place. I hope this is kind of clear. If you have any questions before we move on to the next module.
Yeah, sure, we can continue.
Okay. Perfect. Now, the next thing we're going to, this is quite a big subject, but for a green belt, we don't have to get into too much of detail, but I'll give you the high level detail on what this means. And of course, when you get time, you can spend a little more time if you're really interested, and then start learning how we do it. This is we call design of experiments. Have you ever used it anywhere? DOE?
I'm sorry, what was that?
Design of experiments, DOE methodology. Have you heard about it, or have you used it anywhere?
No, I have not.
Okay, this is a very, very interesting framework or to identify the relationship between key x's or key variables or drivers in a process versus the total output, which is y, right? So y can be a function of x1, x2, x3, and number of x's, right? And we already know there are critical x's that we are trying to look for potential causes, and this is very useful for mainly when you manufacture something or you are testing the yield based on certain parameters, right? So let me give you some examples. So in DOE, what we do is we look at different combination of x's, right? Let's say there is x1, x2, and x3, right? 3 different variables, right? And then you have something called y. So for example, let me keep x1 constant and change x2 and x3, right? The proportion of x2 and x3 is changed, and record what is going to be my y. So my yield, right? So we play around with different combination of x's or different proportion of each of those x's to identify the most optimal y or yield that we can get out of the process. For example, so here is one example that we've seen. So let's say I've picked up about 10 trials, right? And 2 variables that we have is temperature and pressure to get a yield. Now we're saying 7 different trials, right? 7 different combinations for 2 different variables, right? So in the first case, we keep temperature as 125 and the pressure as 30, and you get a yield. In the second case, you have 125 and then the pressure is increased to 31, right? And you get an yield. So similarly, you try out different combination of both 2 variables or 2 different measurements of 2 variables, and you measure where do I get the maximum yield. This is called design of experiments, right? We're trying to experiment with multiple x's, different proportion of each of those x's, and see which is the best output that I get, right? For example, a chocolate manufacturing, right? A chocolates might have 10 different ingredients, right? If I mix all the 10 ingredients in the same proportion, I might get one particular taste, which may not be the most ideal taste a chocolate should have, right? I might be mixing ingredient number 1 with X amount, ingredient number 2 with X2 amount, right? And multiple proportions of each of these X's, and I get the most optimal solution. So how do we get to that particular solution? We have to repeat, or we have to do multiple of these trials with different combinations to get the final best available option. Is it confusing?
It's not. Okay, so through each trial, so basically you're changing the x value to try to obtain the highest yield, y value.
Right.
So you just keep doing trial runs and changing the x value until your y value hits a optimal level.
That's right.
Okay.
That's right. So if you see this graph, right? So I plotted pressure in this y-axis. So you have 5 different pressure levels, right? And then you have temperature. I have about 6 different temperature levels. And these are the 2 variables that I have. Now, it can have multiple combinations. For example, I can have pressure is 120 and temperature is 30. I can have 125 as pressure. I can still have 30 as the temperature. So this could be one combination for me. 130 and 33 can be another combination. So I'll get a point somewhere here, right? And then for each of these combinations, I also measure what is going to be my output, right? So in this case, that bigger line that we see, the total output is 75. Even though the pressure and the temperature is highest for this particular one, the output is only 75. Now, which is the best one? 90 or 95, 92, yeah, somewhere here, right? So we see 121 is my pressure level and 33 is my temperature level for the most optimal or the best yield that possibly I can get. And this is called design of experiments.
Right. Okay.
Try multiple combination basically, right?
Yeah. Okay.
Yeah. Now, at a very high level, there are 2-3 different types of DOEs that is used. And there's something called full factorial DOE, which means if you have 2 variables with 5 different levels, right? You try out all the possible combinations and then you choose the most optimal one. This is good for a small number of variables and small number of combinations that is there. It may not be the most effective in terms of cost, right? We will end up spending more money in doing the experiments. So in a fractional factorial thing, again, we do a sampling or we do an average of certain measurements and then we conduct only the key ones and then come up with the output in variable. However, in fractional, there's one more thing that we check. In full factorial, we are only worried about the yield, right? Which is the highest yield providing. In a fractional factorial method, which is introduced by someone called Taguchi, what they do is they also look at the average value, the mean of the output. For example, for one particular combination, right? If I'm doing multiple trials, you might end up getting different values, which means there is a variation. So we pick up the average there, right? So not just the best output, we also trying to reduce the variation as much as possible, right? And in the response surface method,
Right. You're just trying to get the highest yield at the most optimal point, right? So you check your inputs to see both inputs, your X and Y value, to see which has a greater yield, right?
right? So so yeah, that's right. So that's where you find the best output yield, right? But in some cases, let's say, let me take the chocolate example itself, right? The yield which comes on in a winter season, right, may not be very good during a summer season. For example, the chocolate might melt during the summer season, right? Mm-hmm. So even though the output was so high and we took it, manufactured the chocolate thinking that this is the best output, during the summertime that chocolate completely failed, right? There might be variation due to external factors, right? Those factors are called noise. So there are 2 ways of doing. One, avoid all the noise and then run your experiment. You will get the best output. Second, include your noise and then take the average number and look at, also study the variation that's going to happen over a longer period of time or different seasons, or repeating the same activity. Are we going to get same amount of yield even if we repeat the same thing? So there are the different factors people study. So you don't have to get into so much of detail, but we can just understand how this is done. Okay, so this is an example of full factorial design where all the combinations are tried. So in this case, there are two variables with two different combination, which is 300 and 350. We will try all the options. So 1, 2, 3, 4, 5, 6. So all these combinations will be tried and pick up the next best one. So this case, the full factorial thing works because it's hardly two variables and two combinations, right? It works. But for a larger number of x's, and that actually gets multiplied by something like this, right? 2 square k, or which is the number of options that we have, combinations we have. That can really run into big number. So then we go for factorial, fractional factorial method, where again we do a sampling to choose which one should we, which are the combination we should test. And we also include the average or the variation in the study. So here there are three variables: stop angle, start angle, and fulcrum. And then you have the highest combination of this one, this particular variable. In this case, which is the highest number. So all these are different combinations. These numbers that you see, different combination, and then you select the best possible output. Now, here, there's another concept that you should know. There are two kinds of effect, right? One is main effect, and then interaction effect. Main effect meaning, let's say there are three variables that we're trying to study, right? Not only the interaction of different combinations in start angle with stop angle and fulcrum that we study, we also get which is the best measure of start angle, which is the best measure of stop angle, which is the best measure of fulcrum, right? That also we see, which means that individually we are looking at each variable and calculating the number. And that's called main effect, which means which factor has the largest impact on the output. Currently, we were only looking at yield, right? These three put together, what is my best output? Here, we'll also study for each of this variable, which is the most optimum number. That is called main factor. Okay. Do you have any questions here?
So let's see. Which factor has the largest impact on the output? So factor on the output response. That one has the, it seems that has a greater slope.
Yeah. So this
The
is
fulcrum.
-1 to 1, right?
Yeah.
So obviously,
Well, both okay. So both of them on the x value, both of them are -1 to 1. However, the slope is greater on the fulcrum.
yeah.
So it has a greater relative effect on each factor.
Yeah.
To the output.
The highest of this, a little lower of this, and lower value of this. This would be the best yield that we will be able to get, right? So this value plus this value plus this value would give us the best output.
Okay. Okay.
This is a mathematical equation. They're trying to show a plus b square is equal to c square or whatever. So these two factors put together, we get the output y. Right? Okay. Any questions? These are different kind of interaction that's shown between variables.
Okay.
Okay, so this is one way of coming up with a solution to a problem, right? We design an experiment table. We put all combination of different x's in place and see which is the best output, right? And then we come up with a solution. So define the practical problem, establish an experimental objective, select output variable, select the input variable, which is nothing but your x's. Choose the level of input variable, select the experimental design, execute the experiment, then collect the data to see if this is really, which is the best output. Analyze the data from the designed experiment, draw statistical conclusions, and draw practical solutions from statistical solutions. Then replicate or validate experimental results and implement solutions. And so this is another very effective tool which can be used to identify solutions. So we've seen Fmea, we talked about 5S as a tool. And then we also have seen, we actually spoke about 5Y analysis, which is a great tool. And design of experiments, another great way of getting the optimum result and come up with good solutions. If we have no further questions, we can move on to the next part. So once we have all the solutions, right, it is good that we should also try and put this in a small matrix where we see which of the solutions has the best impact and the most easy to implement, right? So we put a simple matrix. I don't think that matrix is here. So you, on the x-axis, you put ease of implementation. On the y-axis, you put the impact, right? And then we try to plot each of the solutions between these two x's, and whichever comes on the top with, the ease of implementation is quite high, and which gives the best impact possible. So we start putting that as the priority. Right? And that's how we prioritize the solutions to be implemented. If you are able to implement all solutions at a stretch, good for you. But if you are unable to do that, it is always good to have a matrix in place and start picking up one by solution and then start implementing it. Now, before we implement, there is a process that you need to follow. It's called pilot, right? Because any of these recommendations, any new changes that we are bringing to a process can have a huge impact with your downstreams and upstreams. So the first thing what you do is you do a pilot. In pilot, we take a sample. We will not be able to do the entire activity or entire process as a pilot. So for example, if we are placing about 500 purchase orders in a month by a business, we pick up maybe 50 purchase orders, right? 50 purchase orders from different segments as possible, different subgroups as possible. Then we run something called a pilot, right? So what we're doing is that we are doing a testing, and that testing we will do over a period of time. We will not just finish off all these 50 POs in one day. We will, based on the peak hours or peak days in a week, we collect as many different kinds of samples, and we will try and perform the pilot for a month. Right, so this is what it happens in this particular step. testing the functional sigma capabilities of new process where critical solutions defined in the current generation of the generational plan are operational, but on a limited scale. We do it on a very limited scale, right? The primary advantage is limit capital and other resource expenditure, assess true performance of design and solution in a controlled but live environment, identify additional improvements, identify implementation tips and taps, right? And why pilot? There are numerous reasons to pilot: confirm expected results and relationships, increase buy-in, improve implementation, lower risk of failure, improve the ability to better predict, right? So we implement all the solutions, we measure it for almost a month, and after a month we calculate two things. One is your process capability, we also calculate if our metric has improved from where we've defined initially, right? And then we do a report out after a month. So mostly it is done just a month of pilot in a Greenbelt project. Okay, and also we do a monetary saving calculation from the solution. That's something we have discussed earlier, something called business impact. So every project will have a business impact. For example, if I'm improving my on-time delivery from 90 to 95%, I'm creating impact on those 5% of orders, right? These 5% orders might be worth X million or some X amount, and we annualize that for 12 months, and then we showcase that as our business impact. And that also we capture in the improve pilot phase. Ronald, you there?
Yeah, I'm listening.
Okay, so you kind of understand this now, right?
Yeah, I mean it's an upstream activity where you do pilot exercises, scenarios where to assess possible failures, and if so, what would be you can relate it to a dollar value, right? Whether it's savings or it can even be additional costs, that you may have to incur. But the pilot is to, I guess, identify all these to see if your processes are efficient and effective, to essentially implement them in your organization, and then you also put a dollar sign. You associate a dollar cost to them.
Yeah. Excellent.
So you implement the pilot, you implement the processes, you measure the processes effectiveness, and you identify any potential risk or failures, and with those failures you assign some kind of categorical level, whether it's low, mid, or high, and you tie it with any possible cost savings.
Right. Okay. These are some guidelines on when do we do a pilot. You obviously do not want to do a pilot when there is a huge escalation happening in the process. So you wait for a little more stable period. So that's one simple rule that you can keep in mind. And what are the things that you need to consider when driving a pilot?
Yeah, so basically what I mentioned, there was this type of exercise, you do these analysis in upstream activities, whenever you're about to launch a new product or service line, or you're going to launch a new project. You basically do these type of activity exercises to understand, basically to identify any potential risk, and verify that your processes that you have in place are effective or not. If not, then you need to modify them. It kind of is pretty similar to the Fmea analysis.
Right. Risk assessment, right?
Risk assessment is basically what it is, and ensuring that you have good efficiencies with in your processes. Um, and if you don't, you need to modify them accordingly. But so it's a lot of upstream activities and more preventative control.
Right.
Yeah, that's good.
Okay. And then once we have pilot is done, we again validate the results from the pilot. If we identified any risks, we go ahead and mitigate those risks, put the control plans in place, and then we start implementing the solution. That's what we do in the improve phase. That comes to the end of improve phase, and then we move on to control and project closure. Can we continue? You want a break?
Yeah, sure.
Do you want to break, or can we just continue?
We could take a 5-minute break.
Sure. Okay. Okay. So see you in 5 minutes.
Okay.
Okay. Now moving on to the control phase now. There are a few things that we'll do it here. So once we've done the improvement, right? We did the pilot. We started implementing the solutions, and we again measure it for almost a month, right? What we need to ensure is whatever solutions we've put in place, right? Do we have enough controls so that this solution sustains over a long period of time, right? Now,
Right.
few techniques that we use. First is obviously mistake proofing. We implement the mistake proofing against all the solutions that we've done it. And then we develop standard operating procedures where for all the processes that we've done, because there's a change that's happened to the process. We need to ensure the documentation is in place, and that is shared with everybody who's using the process or who's involved in the process. And then we also do a training plan, right? There could be changes in the way process work. The order in which the process used to perform has changed. Then we obviously need to train the necessary parties. And we also see if this project can be replicated to the other streams of the business. For example, we probably did this project only for a certain number of commodities and worked well for us. We can always go ahead and replicate the same project in other streams as well, right? That's something we will do.
Right.
And do a complete control gate, transition project to process owner. Once project is complete and we report out the measure, the result out of the measure phase, which is again a 1-month window that we usually keep for a greenbelt projects. And then we hand over all the documentation and the results and get a sign off from the process owner. That's what we do.
Okay. Yep. Sounds good.
So one of the key deliverables is going to be project sign off for this. So the first would be developing a control plan, develop SOPs, Tollgate review, and project closure. And that's where we, the realized benefit, right? Again, we calculate, we do the annualized number, and then we get a formal sign off from the sponsor. That's when we call it as a project completion. Now, for putting the controls in place, the first thing that we'll have to do is we again do a statistical process control where we do something called control charts, right? For every process, we do a control chart. And then we put in the control plans in place, and then we do the action items on the practical side of the process. And if there's any process automation that is possible, we do that. And any POC or any mistake proofing methodologies that we can use, we will go ahead and use it. Now let me show you how do you need any little deeper understanding on mistake proofing? It's called POC, where we do improve the product quality by preventing defects. Right? This is part of a lean concept. If you've ever gone through a lean trainings before.
Yeah, I've heard of it, yeah.
Yeah, so there are two states of a defect which is addressed by mistake proofing. So you will just quickly see it. Error about to occur, defect about to occur, that's called prediction. Then you have something called a warning signal. Right? In some of the manufacturing floor, right? You might have different lights, warning lights. You'll have yellow, green, and red, right? The red light comes up when a particular assembly has stopped, right? Something has gone wrong. But there will be a yellow light which will show you that something is going to be wrong because there's a pressure change or anything, for example, right? And that's called a warning signal. And then you immediately go and inspect what is happening. We stop the production immediately, fix the problem, then only we start the production again. We do not wait for defective parts to come out, right? That's called mistake proofing. We stop the operation as soon as we get a warning so that no more defective products gets produced. That's one example of mistake proofing. Now, when we did the process capability, we have seen something. We definitely map the process in a distribution curve, and we also had two things, right? One is lower specification limit and upper specification limit. That was given by the customer. In statistical process control, what we do is we feed in the data, a sample data that we collect for this particular activity. And there is something called a control limit. So you'll have a lower control limit and upper control limit. And that is not assigned by the customer. That is calculated by statistics, right? So we plot a number of data. We plot either direct population samples, or we do a range, we calculate the range, or we do a median or mean of the process. We plot it in a control chart. I'm going to show you how that is done. And then we run a test, right? And it will give you two different limits, control limits, lower control limit and upper control limit. If all these data points are staying within these control limits, means that the process is in control. And what goes outside is only a special cost variation, right? Which means we are able to predict any variation and it is well within the control of the process. If there are too many points outside the control limit, then there are too many special cost variation. Maybe we did not predict some of these common variation and we do not have enough solutions in place, right? So that's now here again, based on the data, we have attribute or discrete data and continuous data, right? Based on that, we have multiple control charts that you can use. You probably don't need to learn all of these, but some of these are very useful. For example, if the type of data is about defects, the number of defects, right? You can either use a C chart or a U chart. If it is a defective, for example, when I say defective, if we are processing an invoice to a supplier, right? There might be multiple defects in an invoice. Payment terms might be wrong, price might be wrong, part number might be wrong. So those are called defects. So we count the number of defects in an invoice process. But if we are saying, we are calling it as a defective invoice completely. Any defect in an invoice, we call the entire invoice as a defective one, then we use some other way of calculating the process control, which is NP chart or P chart that we can use. In a continuous data, if the subgroup in the data, right, if the sample size is just, we are just calculating based on a population without any subgroup, then we go for something called IMR chart. And if there are different subgroups, more than 2 to 5 subgroups, then we go for X and R chart. And if the subgroups are more than 10, then we pick up X's chart. So the calculation here is, the first one is, will plot the moving range of the process. I hope you understand the range, right? The top value and the lowest value, right?
Right.
So it calculates the average of the moving range and then it plots into a control chart. The second one, it does X minus R. X is the mean and it reduces the range. So it captures basically the variation in the process. And the third one is mean and the standard deviation, where you have more than 10 plus variables in it. So I'll show you. Now, let's say in a simple way, only defects is captured. Now, we're seeing, trying to plot it in a control chart. So let's say I'm using C chart. I go to control charts, attribute charts, and pick up C. Right? So these are the UCL and LCL, right? So these are actually not the defects, right? This for the defects, we are calculating a particular data, right? This is the reading of that particular process, and we are trying to put it in a C chart. So these are the two limits I was talking about. One is UCL and one is LCL, and it is calculating the move. It's actually plotting each of those values here. And this is a mid value. It's plotting it here up and down. If any of these values is beyond this one, that will be a special variation, which means that process is in control. Just one point outside it, probably we need to revisit and identify what is causing that. And again, we put some recommendations to it. I'll, for example, let's pick up an NP chart. So let's say these are the number of samples, right? Let's say invoice in itself I'll take. There were 100 invoices were processed. Out of that, 10 defective invoices were found, which means 90% of the invoices were good, 10% were defective. Then I use something called charts. Let's say I take NP chart. I samples is nothing but this one. I plotted this on a P chart, right? So I have the samples and I have the number of defects within the and here you see just 1 point or 2 points, which is almost touching the control limit. So process is stable here, or is in control because none of the points are going out. It's just the 2 points that is going out of the almost near the edge of the control limit. So you can go ahead and analyze what is contributing this. If required, you can put a control in place. If this is outside, we can say this is a special cost variation that is affecting the overall process. We can go ahead and see if there's anything that we need to do. Okay, so I'll take another example from the continuous data. Now in this case, subgroup size is less than 8. Right, so you have subgroups of 1 to 8 in this particular data, and these are the readings. Let's say I'm measuring length of the process, length of something, so which was the y for our process. So we measured 6.266658, something like that. And then you have different subgroups. Subgroups means we are calculating different kind of samples. So 8 different category of samples we have taken, and then we are trying to measure something from there, the weight or height of that, right? And then the data is obviously continuous because it's measured on a scale, and subgroup size is somewhere here. So I can use a X and R chart. For our chart, so readings is here, and group is what I have it here. Yeah, and this is how it shows up. Right? Process almost within control. None of the points are going out of control limit. Any questions here?
No, it's okay.
It's quite straightforward. We collect a sample data, and then we'll see if there's any subgroup. Based on that, we select a decision of which is appropriate to use, and then we go ahead and run a control chart and see if the process is in control. And this is something which you can use even without a project, right? This is a hygiene that is used on a production or process floor usually. If you're managing a process with a certain metric, it is always good collect a 30 sample data every month and try and put it on a control chart so that you see if process staying within control or not, if the variation is going beyond the upper control and lower control limit. And that's a hygiene that you can keep, which you can implement on the floor. Right, so 2 different kinds of variation that can happen. One is common cause variation, which is a natural variability, and special causes and unnatural variability. Common cause is something we have already predicted, right? And special cause is when something additional comes up which goes above the or beyond the process the control limit. And it's a great metric for you to have it on any of your dashboard calls or metric review with higher officials. It's always good to put this graph so that you get an idea. Okay, so again, we have a little more details on what each of these charts mean. You can read through that when you receive your material. Okay. Any questions here? And next is we go ahead and implement all those control measures that we have taken. So there are different ways in which you can put control to a process.
Okay.
You can do a documentation plan. You can do a monitoring plan. Let's say once we implement a project for the next 3 quarters, right? You can assign some SMEs within the team to monitor X number of data point to see if process still in control or not. Is the implementations working? Or can we put any sort of warning signals if there is a metric that's going beyond certain limit, and will be triggered to the top management, and will you get a trigger? Whoever is doing the project, is he going to get a trigger? Those kind of controls we can make sure. Aligning systems and structures, documentation plan, monitoring plan, response plan. So if there is a problem, how do we respond to that problem, right? And then there's a training plan if there's change from the recommended action or control plan. Then how do we train those resources, etc. So we can put those. So we've almost come to the end of the session.
Okay.
Any questions?
I can't hear you.
Okay, so let's do a quick recap of what we've learned so far. Would you like to give me a quick overview of what you've done in each of these cases?
Well, this is something that I guess this methodology can be applied to this DMAIC methodology can be applied to. I think it's more applicable from a top level, or like whenever you're about to launch a project or even a process. But you can also what I realized you can apply it for top level, upper management to very from macro to micro. Even you can apply this to even just processes within a department. To measure and control and optimize. So in define element, we were able to first identify what is the problem, what's the voice of the customer, what are their upper and lower specification limits that are going to be given to us by the customer, how to do high value stream mapping, how to optimize process mapping, the importance of process mapping, to detail it, to define it, to understand it, and you can review that and then try to improve on those process mapping.
What comes in a project charter?
The project charter, it's usually you state the problem, the issue, you describe the problem, you describe a solution for it, you describe.
So there's no solution in project charter. So what? Let me just give you a recap. So in project charter, first thing is we had the VOC from the customer. We converted them into a critical quality measures, right? So we identified the key metric that is a key problem from the customer. Then we try and build a business case at an overall, which is the business we are going to manage this project for, and what if we don't do this project, what would be the impact of having this project in place. So that's something we list out in the business case, and from business case we arrive at a problem statement which is more specific. In the problem statement we clearly define from what period to what period what is a metric,
Yes.
what is the problem, and what could be the impact in terms of monetary or whatever that we can say in the problem.
Yeah. So maybe I was confusing it with the problem statement, which is basically it's a document, right? It's a document that you fill this out and you put the problem description, the possible solution or whatnot, or you put from what date to what date it's going to be measured and what's the impacts of this problem, and yeah.
Yeah, and it's a very critical document because that's what will drive us to the rest of the projects, and it becomes very easy to communicate to the right people on what our problem is and what is the impact of it and what is the quantity of the problem that we are seeing.
It identifies who's a person responsible too, right? Or the department.
Absolutely, yeah.
So it kind of lays out the issue, the description of the issue, the date. You put dates in there from what period to what period, how it's going to be impacted, whether it's operational or with the monetary value, and it puts a person responsible.
Right.
And then
is a stakeholder analysis. Stakeholder analysis is nothing but identifying who's going to be your sponsor in the project, who are the key people should be taking the decisions to help you with the project, and what are the things that will keep them happy, right? And
who does what?
Management is very important, right?
Yep. So we got that, and let me 1 second. Let me.
Can we do a high-level process map in SciPoc?
Yeah. So let me 1 second.
Sure.
So yeah, we do the SciPoc models, just suppliers, inputs, process outputs, customers. Do the process maps. We could do level 1, level 2. Level 1 will be like top level from an organizational, operational view, beginning to end. And then level 2 is a more detailed, more like you can even apply like level 2 to pretty much any department. It's more micro perspective. So we did that. We did the reviews, timelines, project milestones, and Gantt charting, which that's what we do here at my job, especially Gantt. All three of them: timelines, milestones, and Gantt charting. And then we review the metrics. We see to see if we're adhering to the timeline, to see if we're going to be able to meet those milestones. If not, what are the risks? What are the potential? What are the elements that are impacting us not reaching those milestones? And what can we do? After that, we address the points and we develop contingency plans to ensure that we meet those milestones. Measuring data, determine the process capability, measuring different gates, understanding central tendency, what's normal distribution, which sits above anything above 0.05. It's normal distribution. Then we have abnormal distribution, which would be pretty much data outside the upper and lower control limits, specification limits.
What's DPMO? Some of the terminologies that you need to keep in mind, how DPMO is arrived at. Z-score in the process capability, a CPK. Those are all there in the document, which you can go through because
the CTK, which is the DPMO, I guess the defects, and we did the critical to quality, which we do first identifying the voice, and then the customer, but then we go to critical to quality. We create the problem charger from there. We can apply the RACI model as well. We review defects, defects per unit or first time yield, which is how many successful builds by output went through the first time. That's when you're measuring the data, and how many defects for defects like DPU, how many defects are there in process per million. To better understand it, when we're measuring data, then the next step we'll analyze it. So the measuring there's different ways to measure the data, but in analyzing the data, use the RACI model, the SMART model, CPOC model, like I mentioned.
And measurement system analysis.
The what, I'm sorry?
The measurement system analysis, MSA.
Yeah, the MSA, we did during the measure with process.
I remember what are the
Six Sigma,
what are the two kinds of variation?
Two types of variations is we have no, I think I'm confusing it. We have two types of data, right? Continuous and
no, I'm asking about two types of variation.
Oh, abnormal or normal?
No, two kinds of variation which contributes to the total variation. So one is process variation, the other one is measurement system variation, right?
Mm-hmm.
These two put together, you get the total variation. And in measurement system analysis, what we do is we try and identify what is the measurement system variation. So even before you collect the data, you fix your gauge, you fix the operators, and you minimize that variation so that from the total variation, you only have process variation left, which is something you can go ahead and study further. So keep that.
Okay. Okay. So let me see. Variation. Okay. We got process variation.
Yeah, it's process or product variation.
Okay.
Second, measurement system variation or gauge variation.
Yeah, I got that. The measurement system, the MSA.
And these two put together is called the observed variation or the actual variation.
Actual, yeah.
So you minimize measurement system variation by doing a gauge study. You remember we did identified repeatability and reproducibility.
Yeah, right.
So same part number, same equipment, same operator doing it multiple times will give us repeatability. Multiple operator measuring the same part will.
But you change the X value, you change the operator, you change the tool, the equipment.
Yeah.
To basically just to zero in to identify whether it's the X or the Y, either it's the operator and the tools that we're using, or whether it's a process or it's a product.
Right.
To better understand where your defects are coming from.
Absolutely.
Yeah. Mm-hmm.
And when we move to the analyze phase, we do process mapping. Also, we get into a room, do a brainstorming, see which are the possible X's through a fishbone analysis, right? A cause and effect. And then we collect data around all those X's. And in the analysis, what else do? We plot
do the
it on
FMEA, the failure mode effective analysis, which consists of.
Before we do the FMEA, in the analyze, we have to, from the total X's, we have to come up with the critical X's, right? So we first do a box plot operator, right? And see which of the X's are critical. And we also prove it by using hypothesis testing.
Yes. Yes.
right? And wherever p-value is below 0.05, we prove it as saying that this is a significant X.
Yes. So yeah, so through the hypothesis model testing, you basically is to identify if it's lower than 0.05, then you can see that a particular X value, it's a critical one. So you want to identify the critical X value, and you can apply the 80-20 rule. You know, so you can say, okay, we need to focus on these X values. So essentially, what you're doing is you run your reports, you gather the data, measure it, you run your reports, and now we analyze it to see, is it worth it? Or first of all, we need to just to identify what are my major X values that are impacting or driving a high yield, and is it necessary? Is it beneficial to address those X values? You know, and sometimes it could be that you have 10 different X values, but two or three are 80% of the root cause. So you're like, okay, well, we need to focus on these two or three X values, or it could be where it's pretty much evenly spread out, so it's not the X value. You don't have no critical X.
Right.
Okay.
And then we move on to the proof.
Yes, after that, you can do the Fmea, the failure mode effective analysis, where you have two different types. You have process and design. Just a tool to evaluate potential failures. So that's a very good analysis that you can do before launching a project, before launching a product or service line, or even before launching a process. And we did that. You showed me the Excel template where you input the data and define the severity on it. You grade it based on the formula, and then you implement a control or a way to improve or control the situation. Then it gets graded again. So just ways to understand in risk assessment, basically.
What are some of the tools for identifying solutions?
I'm sorry?
What are some of the ways in which you can come up with solutions? We can do a brainstorming.
You do a brainstorming session with different stakeholders and try to come up with ways to improve.
5-way analysis.
The what, I'm sorry?
5-why analysis.
Oh, the 5 whys. We just ask why until you come to a final solution.
We can do a Kaizen, 5S, non-value.
Kaizen, 5S, sort, set, shine, standardize, sustain. You can do the 5 why model, the 5S. You can do value stream mapping or value added analysis. Those are ways to improve. Basically, just different Kaizen tools, continuous improvement tools.
Right.
Mm-hmm. And we also looked at the DOE, design of experience, full factorials, and usually if it's the main one that we reviewed was more like the full factorials, which is 2 to 5 input variables. We reviewed the Pokyoka, basically lean manufacturing, mistake proof.
Before Pokyoka, once solutions are identified, we communicate it to the stakeholders and get their approvals. And then we go and do a pilot, right? So we create a plan. We run the pilot for a certain number of samples.
Mm-hmm. Certain amount of time.
Right.
Mm-hmm. So You launch it, you get the approval from different stakeholders and say, okay, so now you run the pilot of the process. Let's say it's a process that needs to be improved. You run the pilot, we're going to do this pilot. These are going to be the stakeholders involved. This is the process. And we're going to measure it from, it's going to run from, for 6 months. We're going to put a person in charge to monitor the process, to monitor the progress. And we should also put some controls in there, and we're to alarm, to warn the person in charge that should be monitoring the process and the progress, to see if everything's going within the parameters between the UCL and the LCL. And upon the 6-month period, then we review the data, if the process was effective or not, if it stayed within the UCL and the LCL, and if so, then we have an effective process, and we can move forward with it.
And what's the difference between customer specification limit and control limit?
So the customer specification limit is, they're giving us the parameters. The customer is giving us the parameters that we need to fall within. The control limits, we're identifying the control limits, and we're identifying these parameters.
That is statistics identifies, right?
I'm sorry?
It is identified by the system, statistically given limit.
Yes, but the input by figures and data that we input.
Yeah, we're just putting the data. We're just putting the data, and the system calculates automatically what a control limit is. So
yes.
Yeah. So there's no recommendation from our side. It's done by system, and it identifies special cause variation. Processes are in control or not. Have we predicted all this variation, which we already know, right?
Yeah. So the limit, the UCL, limit, the lower control and the upper control limits. Yeah, but that's what I'm saying. But they're defined by us. You know what I mean? I mean, well, based on the input. Okay, it's not defined by us. I mean, we input the data. Yeah, we input the data in the system, and then based on the activities that take place, you generate the report, and it tells you. System will tell you if you're within or without the control limits.
Right. So it calculates by itself. You know, any unpredicted variation will be captured there. That's the whole point. Special cost variation. Yeah. And you monetize and get the sign off from the stakeholders, then you close the project.
Yes.
Right. So I think that's pretty much the entire DMAIC methodology, but you still have a lot more information in the slides that we will send across. We have a lot of calculations, formulae. You might have some more details on how sampling is done, etc. So you can always go through and study. I mean, it's a big topic, right? You can go to master black belt level and learn a lot of things, but this is pretty much for a green belt level. I think we're good to close the session.
Okay.
Back, any questions? Anything that you would like to pass on?
Not at the moment. Not at the moment. So I guess once you guys send the information over, I'm gonna give it another look and study some more on my own, and then hopefully I can be ready to take the exam.
Great. That's it, Ronald. Thank you. It was a great time in the last 3 or 4 sessions we had. You were very interactive, which made my job very easy. And since you are from the supply chain background, I could also relate to some of these examples, and you were able to get it very easily. Thank you for your time. It was great.
I hope so.
Right.
Yeah. Thank you. Thank you for your time, and thank you for the sessions. I appreciate it, and take care.
Take care, Ronald. Have a great career. Yeah. Bye.
Thank you, you too. Bye-bye.